Okay, let's dive right into this. What does a bronze statue have in common with a hospital IV drip? Or how about a can of soda and the salt we throw on icy roads? It kind of sounds like the start of a bad joke, right? But the answer is actually a fundamental scientific principle that's happening all around us, all the time. Today, we're going to pull back the curtain on the hidden science of solutions. So, picture a classic bronze statue. You look at it and it seems like it's made of one single thing, bronze. But really, it's this perfectly blended mixture, a solution of two different metals, copper and tin, melted together. And that creates an alloy that's way stronger than either one could ever be on its own. Or think about an IV bag you'd see in a hospital. I mean, it looks just like water, right? But it's actually a life-saving solution. It's a super precise mixture of salts dissolved in water, and it's been engineered to have the exact same concentration as your blood. If that concentration is off by just a little bit, well, the results can be pretty disastrous. And that can of soda, you know that psh sound when you pop the top? That is literally the sound of chemistry happening. Inside that can, a whole bunch of carbon dioxide gas has been forced under some serious pressure to dissolve into the liquid. The second you pop that tab, you release the pressure, and all that gas makes a break for it. And that's what gives us that fizz we all know. So, let's recap. We've got a solid metal statue, a life-saving liquid, and a bubbly drink. What in the world could they possibly have in common? I mean, they seem like they're from completely different planets, but they are all built on the exact same scientific idea. That's it. They are all solutions. That is the one thing that connects them all. And a solution isn't just something you mix up in a chemistry lab beaker. Nope. It's any mixture where different things are so perfectly blended together that they just look like one single uniform substance. From the air we breathe to the oceans themselves. They're literally everywhere. So how do these solutions actually work? I mean, what's going on at the molecular level? To get that, we need to meet the two key players in this little chemical dance. The thing that does the dissolving and, well, the thing that gets dissolved. Okay, first up, you've got the solvent. This is the main event. The substance that's in the largest amount, it's the one doing all the heavy lifting, the dissolving. Think of the water in a soda. And the stuff that's being dissolved, that's the solute. That'd be the sugar, the flavors, and that CO2 gas. You put them together, and boom, you've got a solution. It's really that simple. Now, in science, and especially in medicine, just saying you have a little bit of sugar in your water, that's just not going to cut it. We need to be way more precise. We need to talk about concentration, which is exactly how much solute is packed into the solvent. Because the difference between a little and a lot can literally be the difference between a helpful medicine and a deadly poison. So on a really basic level, we can talk about solutions being dilute, not much solute, or concentrated, where there's a whole lot of it packed in there. But to really see why measuring this stuff precisely is so critical, let's look at a pretty powerful real-world example. So in a lot of places, a tiny amount of fluoride gets added to our drinking water. At a concentration of just 1 part per million, which is like one single drop in a whole bathtub, this fluoride is a hero. It makes our tooth enamel stronger and helps fight off cavities. Pretty great, right? But watch what happens when that concentration just barely ticks up. You push it past 1.5 parts per million, and our hero becomes a villain. The exact same fluoride becomes toxic. It can mottle your teeth, and at higher levels, it's an actual poison. So the crucial point is, precision matters a lot. The good news is solutions aren't just chaotic messes. They actually operate based on a set of really predictable physical laws. And once we get a handle on these rules, we can use them to do some pretty incredible things, from making the perfect fizzy drink to keeping deep-sea divers safe. All right, let's start with Henry's Law. This one's pretty intuitive, actually. It just says the more pressure you put on a gas, the more of it will dissolve into a liquid. That's exactly how soda gets made. They crank up the pressure to pack all that CO2 in. But it also explains a really serious medical issue for divers called the bends. Next up, we have Raoult's Law. And this one reveals another really cool behavior. When you dissolve something like salt in water, the little salt particles basically act like tiny roadblocks right at the surface. They literally get in the way, which makes it much harder for the water molecules to escape and turn into vapor. This one simple idea has some amazing consequences. And what's really interesting about this is that simple act of just making it harder for water to evaporate, well, it unlocks some incredible real-world superpowers that we use every single day. These are something called colligative properties. And here's the really mind-blowing part. For these properties, it doesn't matter what you dissolve. It could be salt, it could be sugar, it could be anything. All that matters is how many individual little particles of that solute you add to the mix. The more particles you dump in, the stronger the effect. It's about quantity, not quality. So these colligative properties give us two major superpowers. First, freezing point depression. By adding salt particles to water, we make it harder for that water to freeze, and that's exactly why we salt icy roads in the winter. And second, boiling point elevation. Adding a solute also makes the liquid harder to boil. This is the whole idea behind the antifreeze in your car. It raises the boiling point of the water in your engine so it doesn't overheat in the summer. But maybe the most important superpower of all is something called osmosis. The best way to think about it is like nature's balancing act. So imagine you have a barrier, but it only lets water through. If you have a weak, watery solution on one side and a strong, concentrated solution on the other, water is automatically going to flow towards the concentrated side to try and dilute it and even things out. That natural flow, that's osmosis. And this brilliantly illustrates why understanding solutions is literally a matter of life and death in medicine. Our red blood cells are surrounded by one of those membranes that only lets water through. If you put them in a solution that's too salty, a hypertonic solution, all the water rushes out of the cells and they shrivel up. If you put them in a solution that's too watery, a hypotonic one, water rushes in and they can swell up and actually burst. And that is why IV drips have to be isotonic, a perfect 0.9% saline solution, to keep the water flow perfectly balanced and our cells happy and safe. So we've seen the rules that make solutions tick. But this isn't just stuff for a textbook. These very same principles, especially osmosis, are at the very heart of how we solve some of humanity's biggest challenges. From ancient problems like how to keep food from spoiling, to modern crises like finding fresh water. For thousands of years, we've preserved food by curing it with salt or packing it in sugar. What we're actually doing is we're weaponizing osmosis. This creates a super salty or sugary environment on the food, so when any unlucky bacteria happens to land there, osmosis viciously pulls all the water right out of them. They completely dehydrate, shrivel up, and die. It's a brilliant, ancient way of using chemistry to keep our food safe. But what if we could beat osmosis? What if we could flip the script? Well, that's exactly what we do with a technology called reverse osmosis. By applying a ton of pressure to seawater, we can overpower that natural flow and literally squeeze pure water molecules backwards through a membrane, leaving all the salt behind. It's a totally ingenious way to turn the undrinkable ocean into fresh drinking water. So, the next time you salt a road, open a soda, or even just drink a glass of water, just take a second to remember the incredible, invisible science that's at play. Solutions govern our bodies, our food, our planet. From our blood to the oceans, they are absolutely everywhere. It just makes you wonder, what other invisible science is hiding in plain sight?